お待たせいたしました。では続きましてのスピーカーご紹介いたしましょう。次のステージはウェイハン・ウンさんです。Next, we'd like to invite our next speaker, Mr. Wei Han Un. The floor is yours.
All right. So I believe most of you would have heard of something called the Pareto principle, the 80%, 20% rule. It basically states that 80% of the outputs come from 20% of the inputs. So for example, a company's revenue, 80% of it comes from 20% of its customer. And perhaps another example that's perhaps closer to you is like 80% of your personal productivity comes from 20% of your effort. And magically, this also applies to Ethereum. So we found out that 80% of Ethereum state hasn't been touched in a year, meaning 20% of the current Ethereum state is considered active. So think about it, when was the last time that you transacted? Or when was the last time that you transacted on all of your accounts? And it kind of makes sense based on these statistics because think about it, the first time that you entered the Ethereum space, right? You probably wander around, play around with some wallet on your desktop and, you transfer some funds, play around with some smart contracts. And the more that you understand about this space, the more that you figure out that, I have better wallets that I can use. I have better alternatives that I can use. So what you do is that you transfer all of your funds, your USDT, USDC, your ETHs, whatever, your NFTs to another account. And what happened to your first account? You just abandon it. But even if you abandon it, the account's still alive on chain, but it's considered garbage, right? So when we figured this out, we want to take a data-driven approach on core protocol development, or in particularly, we want to understand more about the current state of access patterns, how does access patterns work in terms of like Ethereum state. So we actually found out a few interesting discoveries, and we also had a few ideas on how to improve L1 scaling and improve the user experience on Ethereum based on the discoveries that we have. But before that, let us rewind a little bit and understand what exactly is a state. So when we refer to state on Ethereum, we are usually referring to accounts. So accounts in Ethereum has two types. One is externally owned accounts, EOAs, and another one is contract accounts. So for each contract account, they will also have its own storage slots. So each slot is 32 bytes. Whatever you want to put in the 32 bytes, up to you. It's up to the app developers. And another one is also on the bytecode. So every account would also have its own bytecode, right, which is basically your contract code, right? So one key thing here is that the number of accounts and the number of storage slots can grow infinitely. And it's actually not infinite. I mean, the actual number is 2 to the power of 256, which is a very large number if you try to Google it. So yeah, that's why I say it's called infinitely. And so that applies to both accounts and storage slots. When you have this kind of scenario, you will lead to something what we call as the problem of state growth. So currently, as of right now, on Ethereum, mainnet, we have about 300 million accounts, probably more than that already. And we have about more than 1.3 billion storage slots. When you run an execution client, for example, Go Ethereum or Nethermind, these numbers would probably translate to about 110 or to 120 gigabytes, only in terms of like account and storage slots. If you were to consider Merkle Parashah Tri data stored in execution clients, that number will probably go up to about 300 to 400 gigabytes. And the problem here is that the numbers will only keep growing, right? When we scale L1, when we increase the gas limit, when we increase the throughput, that means that the state will grow, right? And it will grow faster than ever. So why do we care about state growth? Number one is the storage space. This is pretty obvious. So if you need to store more state, you need to upgrade your hardware. That means you have to change your SSD every 5 years or every 10 years or whatever. So changing your SSD every 5 years or 10 years is not that bad because hardware will degrade anyways. But another problem that is more important to solve, in my opinion, is performance. Because as the state grows, the underlying structure, cryptographic structure behind the state, behind the accounts and behind the storage slots is Merkle Parashah Tri. And to represent a Merkle Parashah Tri or MPT, internally in execution clients, they will have to store all of the nodes in the database. So as the state grows, as the MPT size grows, it means that the try depth, the try levels, the number of levels in the try grows from, for example, 5 to 7 or even to 10. So when that happens, it will affect the performance of the execution clients. So that also means that as the chain progresses, assuming that you don't change your hardware, your performance of the execution client will be worsened, right? So that's another problem. And I think the third problem that I can see here is syncing, right? Right now, let's say you want to sync a node, it will take 1 day on Go Ethereum or Nethermind or other execution client. But what if the state grows larger and larger? Then it will take more than 1 day, maybe 2 days, or depending on the hardware, I don't know, 1 week, 2 weeks, or whatever. So this is the general overview of state growth. And when we want to tackle this problem, we have a few angles. And one of the angles that we want to take is on the side of data. So we want to analyze the state. And the first question that we ask ourselves is all state equal? And from the title of this talk, you already know that it's not equal. And let's look at a few discoveries. So the first question that we wanted to answer is EOAs versus contracts. Which one lasts longer, right? So from this graph, right, on the left side, bottom left corner, I mean on the x-axis is all the activity span. Basically, you have single block, less than 1 year, 1 to 2 years, 2 to 3 years, so on and so forth. I'll explain more about that later. But first, the first observation that we found is EOAs last longer than contracts, right? So this is a pretty interesting one. And it kind of also makes sense because most of the users right now, they will have to transact using EOAs, not smart wallets or account abstraction wallet yet. So naturally, I mean, you will transfer EVs or you would interact with contracts. So typically, EOAs will have more activity compared to contracts. But here's the interesting thing, right? 55% of the total contracts operated for a single block. What does that mean? It means that, let's say you deploy a contract, you execute it, you call or whatever, you play around with the contract. 55% of the total contracts only operate in a single block, meaning they only deploy and they only do whatever execution only in a single block. And we have never seen any activities from them apart from that single block. Now, this is pretty stunning, at least for me, when I first discovered it. And the second thing is that most accounts operate for less than a year. So we still have to investigate why is that the case, but there could be a few speculations. So the first example is that, for example, if you're a user, you first own a EOA account, then you realize that, I want to transfer to a centralized exchange, then you transfer to centralized exchange and you just start to transact there and not on your own chain EOA. Another thing could be like for contracts, some teams, some applications, especially those who are successful, sometimes they want to upgrade their smart contract. So what they will do is that you cannot modify existing smart contracts, so you have some sort of like a proxy pattern like Diamond Standard, where you can actually change or so-called upgrade your implementation contract. So there are a lot of reasonings that we have to find out, and the other ones could be like spams, MEVs, bots, or whatever. So the next question that we wanted to answer is how unique are the contracts? We have about 50 million contract accounts right now, but it doesn't mean that we have 50 million applications. In fact, one contract does not equal to one application because, in fact, contracts reuse existing code implementation. So it's split into two categories. We have something called template bytecode, which is basically code that's being deployed by more than one contract. And we have something called what we categorize as unique bytecode, which is bytecode deployed by exactly one contract. So first thing, majority of the bytecodes are unique. We have 50 million contracts, but yet we only have around 1.6 million unique code implementation, right? So that's number one. And number two is that in terms of the template bytecodes, it only makes up about 9% of the total bytecodes that we have. So, but yet, most contracts are deployed using templates. So remember the number just now, 9%, we only have 9% of template contracts. which is about 150K. But this 150K code implementations are being reused by 97% of the total contracts on Ethereum right now. Meaning, most of the contracts on Ethereum right now just reuse existing code implementation. So again, there are a few speculations. We have to still continue to investigate. But a few that came into my mind, obviously, is spam tokens. People just deploy tokens to spam or to phish or to scam people or whatever. Another one that I think I'm speculating is also on MEV side. So maybe reuse strategies or whatever. Yeah, but this is something that is worth to find out. And the next one further solidifies that why I think most of these are spams or scams is that when we look at the activity span in terms of the median level, the template contracts, the unique contracts operate 2 times longer than the templates, right? So it kind of further solidifies that the template contracts that are deployed from existing code implementation, they are mostly spams or scams, yeah. Right. Next thing, similar to the accounts, we also wanted to know how actively used are the storage slots. And the first immediate observation that we have is 63% of the slots only operate for a single block. So it's the same thing, right? It means that somebody has written storage slot or read that storage slot only in a single block, right? It could be off-chain read, or off-chain read, but we don't know. We only know about on-chain. But 63% only operate for a single block. And most of them, perhaps more than 80% of them, operate only for under a year, right? So to conclude, right, the findings, most accounts last for less than 1 year, most storage slots last for less than 1 year, and most contracts reuse the same bytecode. So when we have these findings, how can we utilize this information to come up with some solutions or ideas to improve the Ethereum protocol? So there are a few ideas. The first idea is state expiry. So this has been in ongoing research and development for a long time. So it started almost like 10 years ago. So the core idea of state expiry is simple, is to expire now and revive later. We know that there are a bunch of garbage state on Ethereum right now. So we want to remove all of this. But let's say if users want to revive it, or want to restore it, they can submit a transaction with the proof, and yeah, the state is back on chain. So by doing this, we can stop or even slow down state growth. Yeah. So we did a very simple analysis. We compared for full state versus 1 year state on one of our execution clients, Go Ethereum, and we managed to see like that particular execution client or GAF node, which only stores like 1 year worth of state, it managed to save like 80% of the storage space in terms of state. So that will also help with performance. Next, we also have another idea of introducing something called temporary storage model, where it's basically the same as the permanent storage model that we have, except that every 6 months or every 1 year, let's say, it will be automatically emptied out. So what happens is that why would contract developers want to use this? Well, if you are fine with your state data being deleted after 6 months or after 1 year, then you can use this. Why do you want to use this? Because most likely the opcode of storing this the state in this temporary storage will be cheaper, right? So maybe that's one good incentive. And then the next thing they want to do is also to make contract deployment cheaper. So when you deploy a contract, there's a bunch of things that you need to calculate when it comes to calculating the gas cost of contract deployment. And one of it is code deposit cost, which is 200 times code size in terms of bytes. So again, from our analysis, most contracts, you reuse the same bytecodes. And bytecodes are deduplicated in EL clients, meaning when you have 2 contracts which shares the same code implementation, when you actually store it in EL clients, EL clients wouldn't store duplicates of them. You actually store a single unique implementation of the bytecode. So why is it that users, when they deploy contract, they have to pay this code deposit cost as well? Well, we can actually make them cheaper. So there are a few solutions that we can have. The first variant is what I call a same block duplicate discount, where in a block, let's say if a bytecode appears more than once, then the first one would pay the full gas cost of contract deployment, code deposit cost, and the subsequent ones doesn't have to pay the code deposit cost. One immediate disadvantage is that it's unfair for the first one, and since it's unfair, then it becomes like an ordering game where people fight not to become the first one. And the second one is what I call as global code hash registry. So you basically introduce a system contract storing all of the code hashes that ever exist. So all contract deployments first check if the bytecode exists. If it exists, then you don't have to pay the code deposit cost. If it doesn't exist, then you have to pay it. So pretty straightforward. And so we basically have like some of the findings that we have. Most accounts last for less than 1 year, storage slots as well, and most contracts reuse the same bytecode. And from that kind of like a data-driven approach, we managed to come up with a few ideas. And this is actually not all. We'll be publishing an article on ETH Research later on all of the findings that we have. This is just like perhaps like 50% of what we actually found. So, but the point here is that this is only the tip of the iceberg. We don't fully understand everything about state access patterns on Ethereum right now. So if we can understand more, we can come up with better solutions that can actually help to scale R1 and also to improve user experience on Ethereum. So ultimately, this is my belief. I believe that not all state is equal. And I also believe that our protocol shouldn't treat them as if it were. And by doing so, I believe that we can make Ethereum cheaper, faster, and more sustainable. So thank you.